Our topic is 4 inputs priority encoder. A priority encoder is an encoder circuit that includes the priority function. The operation of priority encoder is such that if two or more inputs are equal to 1 at the same time, the input having the highest priority will take precedence. The truth table of a 4 inputs priority encoder is given below. In addition to the two outputs X and Y, the circuit has a third output designated by V. This is a valid bit indicator that is set to 1 when one or more inputs are active. Now the truth table in the condensed form is shown in the figure. On the left side we have 4 inputs D0, D1, D2, D3, and on the right side we have 3 variables 2, X, Y, and 1 variable V, which is the valid bit indicator. And if the input is valid, then V will be equal to 1, and if it is not valid, then V will be equal to 0. Now in this truth table, the first row consists of 0, 0, 0, 0 because it is not the valid input and therefore V is 0 state, and we can take don't care condition on the variable X and Y. Now in the second row we have D0 is equal to 1, and therefore at the output we will get binary code of 0. Then in the next row we have don't care condition, and then D1 is equal to 1 state. So at the output we get the binary code of 1. Then in the next state and next row we have 2 don't care conditions D0 and D1, and we have D2 is equal to 1 state, and therefore at the output we will get code of binary 2. Then in the last row we have 3 don't care conditions, then D3 is equal to 1 state, so at the output we will get the binary code of 3. Don't care condition is useful to draw a truth table in the condensed form, but if we draw the truth table in the expanded form, then it is shown in the figure, and in this figure all the combinations are shown. So first in the first row we have 0, 0, 0, 0, and at the output X, Y are don't care condition, and V is equal to 0 because it is not the valid input. Then in the second row we have D0 is equal to 1 state, so at the output we will get binary code of 0. Then in the third row we have D1 is equal to 1 state, and therefore at the output we will get the binary code of 1. So in this way all the truth table is drawn, and in the last row we have 1 1 1 1, and it is a priority encoder, and therefore the priority is given to the higher subscript value. So at the higher subscript value we have D3 is equal to 1 state, and therefore this 1 is considered, and output is a binary code of 3. Now we will draw K-maps for x and y to simplify the function, and we are looking that we have 4 inputs, and therefore for 4 inputs we have total number of squares of K-map will be 2 raised power 4, which is equal to 16, and now we are drawing a K-map of 16 squares. Now we will write 1 in the particular square of K-map, and this can be done by looking column of x in the truth table where x is equal to 1. The corresponding minterm is noted, and that minterm is written in this K-map, and for that minterm we will write 1 in the corresponding square. So in this way all the minterms, for each minterm we can write 1 in the corresponding square. So we have the K-map as shown in the figure. Now in the second row we have in the second column we have 1 1 1 1. Similarly, in the third column, we have again 1 1 1 1. In the third column, we have again 1 1 1 1. Now we are making groups of the adjacent squares, and we have 2 groups each of 8 squares. So in the first group, we are looking that if we move from top to bottom, then the variable D0 and D1 are changing. So these 2 variables can be neglected. And if we move from left to right, then we are looking for the first group that the variable D2 changes, but D3 does not change. So we can write x is equal to D3. Similarly, in the other group, if we are moving from top to bottom, the variable D0, D1 are changing. These 2 are neglected. Then if we move from left to right, then we are looking that the variable D3 changes, but D2 does not change. So we can write D2. So x will be equal to D2 plus D3. Similarly, we can draw a K-map for the variable y, and then we can write 1 in the corresponding square, and we can see the column of y in the truth table where y is equal to 1. The corresponding minterm is noted, and for each minterm we can write 1 in the corresponding square. So in this way we have 1 1 1 1 in the second column and 1 1 1 1 in the third column, but in the second row we have 2 1s in the first square and the second square. Similarly, we have 1 1 in the third row of the first 2 squares. Now we are going to make groups of 8, which is shown in the figure, and the other group is the group of 4 squares. So we can write y is equal to, first of all we are considering the group of 8 from top to bottom. If we move, then we can see that the variable d0 and d1 are changing. These variables are neglected. Then we can draw its logic diagram, which is shown in the figure, and the valid bit indicator will be equal to addition of all the 4 d0, d1, d2, d3.